Problem solved. So welcome everyone to our seminar today. Today's speaker is Dr. Ranjitha Raviprakash. She recently joined our discipline as a postdoctoral fellow in mathematics. She specializes in pointfree topology, and some context and some background about her. She grew up and she did her undergraduate studies in Bangalore, India. She then moved to the US where she completed her master's and her PhD at New Mexico State University. There were two universities though. And of course, now she's here with us in South Africa. So we look forward to her talk on MT-algebras. MT-Tarski.
Okay, thank you so much. I really want to thank for organizing this. As much as I wanted to present my work, I'm super nervous. So I'm going to present something called as Mckinsey-Tarski Algebras. This has been my work even for my thesis. Let's start with some motivation. So topological spaces are, we all know there are some topological spaces, and if not some topological spaces, you can think of it as just a real line R. It's a very good topological space, but it's a generalized one. So we are always keen on studying the topological spaces algebraically. So there are so many ways of studying topological spaces algebraically. One of them is point topology. So what it basically does is topological spaces, primitive notion, the main object of study are points, right? So what if we study the lattice of opens, the collection of opens, the lattice of open sets, where you're forgetting the points, you're just studying the lattice of open sets. That's pretty much point topology, and that's the theory of frames. But is it the only way? No. So what can be done is, what if instead of looking at the lattice of open sets, we look at the lattice of all subsets? Why restrict to just open sets? So this is exactly how McKinsey-Tarski, back then they just started it, but it just didn't take a direction into point-free topology. So I'm going to be describing how we did it using this technique or generalizing this idea instead of working with lattice of opens, working with lattice of all subsets. So the goal of this talk would be to somehow generalize the notion and make it faithful to the topological spaces and also to frame. So it's not like replacing anything. I just want to present it in a way where MT-algebras fits in the puzzle. The frames exist, topological spaces exist, and how we can fit in both the world. Okay, so there are frames do extend topology, but they are very equivalent to very well-behaved spaces, which are sober spaces. I'll explain in a while what they are, but they're very well-behaved when it is sober spaces. So what the Mckinsey-Tarski algebra does is it captures all the topological spaces, because maybe there are some spaces which are not sober. People are curious of studying what non-sober spaces can be done algebraically. So in order to capture all the topological spaces, the Mckinsey-Tarski algebras will work. This also allows us to do lower separation axioms. So there are so many separation axioms. I don't know the background here, but I'm just gonna point out we have something called as T0, T1, T half, all the separations axioms, right? So, but Hausdorff spaces are common. We all work with Hausdorff spaces. They are sober spaces. But what if there are non-sober spaces? The Mckinsey-Tarski algebras captures that because we can capture all topological spaces and even the lower spaces. So let's start off with an example. I already gave the motivation. The whole talk will be something like this. Start with a space, start with open sets, or work with a power set algebra. So if I take a topological space X, and I take the lattice of opens, now I'm gonna try to start introducing technical, not too technical, but little technical. Omega of X, that's just the lattice of open sets. I'm going to denote it by omega. And that's a frame. And this is how the standard point topology works, right? Frame, omega open sets, lattice of open sets. So the same topological space, instead of taking the open set, I take the power set. Power set algebra is a collection of all subsets, right? That's a complete Boolean algebra. Actually, it's a complete atomic Boolean algebra. Atomic, when I say, you have singleton sets, right? You have all the singleton sets, so it has all those. So this is a complete Boolean algebra. And we have an interior operator. A topological space comes with a topology on it, so open sets on it. That's the interior operator. And we can generalize it, we can invert it by just box. So this is the motivation for how MT-algebra will come into existence. Like instead of working with open sets, you work with color set with an interior operator on it. So this is an example for Mckinsey-Tarski algebras, and I will explain more how P and omega actually play a very big role for us later. So now, this is how I'm going to go about it. We just motivated it. I hope I am motivated enough. Now I'll be defining what MT-algebras are, and I'll be defining what separation axioms in the algebraic setting, in the MT-algebra setting. Like, because we all know it's so difficult to say something is separated when you're not talking about points. Separation comes because you have points and you're separating the points. And how do we talk about it algebraically? That's what we will discuss. And as I said, my goal is not to just make faithful to the topological spaces. The frame theory already exists, very prominent. I want to make sure that all the results I have, all the things I have, will also agree very well with the frame theoretic results. That's why I'm going to go and establish Hoffman-Mislov theorem, dualities for MT-algebras, and stone duality. These are all very well-established theorems in the literature already. Okay. So let me start off by saying what frames are. A frame is a complete lattice which satisfies joint infinite distributive law. So this is my infimum, the wedge is my infimum, and the join is supremum. So whenever I say meet, I mean infimum. Whenever I say join, I mean supremum. So A meet join of S is join of A meet S. So the frame is a complete lattice which satisfies this property. And with this property, we can also say that frame is actually distributive. So, and what about the morphisms? We call something frame homomorphism between two frames if it preserves finite units and arbitrary joints. Meet are infimum and joints. Okay, now we have the object and now we have the morphisms. We are going to define it category. Frames is the category of frames and frame homomorphisms. So if somebody is not seen category theory before, I will try to summarize everything in the slide as much as I can without trying to talk about category theory, and I just want to give a storyline of what is happening. So in this slide, I just defined some category. What category means, it has some object and morphisms. Yeah, that's what I did here. And this is going to be my style throughout, but I'll try my best to summarize without trying to get into technical. So this I already explained. If you have a topological space, the omega of X is open sets. And if you have a continuous map, the same omega of, if I apply the omega to the F, the continuous map, it's just an inverse image map, which gives me a frame omega. So why did I need this omega? The technical thing is it's a contravariant functor. So what does a functor do basically? It's like there you have two different worlds and you want to travel from one world to the other world. So I have topological spaces with continuous functions. That's my world. And the frame is another world. So category theory is a language which makes me travel between the two worlds. That's what the omega does. The omega takes a topological space and sends it to frames. Of course, now we're all curious how to go back, right? So how to go back? We use something called as points. Points can be seen in many different ways. The one I'm using here is completely prime filters. Again, if you don't have to know the technical details, the storyline is a completely prime filters of a frame gives you a topological spaces. So we can travel in topological spaces to frames to topological spaces, and the morphisms also behave very well. So that's the whole story of this slide, where topological spaces and frames are in that. Okay, but that's just, I said, like they go, they come back, right? When are they both the same? Like when, maybe not the same, when are they saying, when can we conclude that what kind of frames, what kind of topological spaces are equivalent? Okay? So for that, I define what is something called a soberity. Soberity. A closed set in a topological space X is irreducible, so you cannot write it as a union of two proper closed subsets. And a space is sober every irreducible closed set, there is a unique point such that the closed set is closure of that unique point. This is the definition of sober. And what is spatial? Spatial simply means whenever it is isomorphic to lattice or open topological space. What I say, like, given a frame, if I can see that frame as some open sets of a topological space, if they're same, that's what spatial means. Okay? So why did I define these two? Every time I'm going to just make sure that I'm following the category theory notions. SOB will be category of sober spaces with the same morphisms, continuous and X frame will be my spatial frames. So, and Docker and Parker were the first one to give this adjunction and dual equivalence. So omega PT, just to remind, we saw that topological spaces to frames, frames to topological spaces. Now, once we have sober spaces and spatial frames, we get an equivalence. So what I'm trying to say is, yes, we have a world to go back and forth, and they both agree upon each other. They act similarly. Once you make this sober, once this makes spatial frames. Okay. So this is the story about frame theory. Okay, so what is Mckinsey-Tarski algebra and how can we get into this? So in 1944, McKinsey and Tarski actually introduced what is called as interior algebra. So what Kuratowski in 1920s he did was, you have a topological space, you take the power set algebra of that and you put a closure operator on it. Closure operator or interior operator, the both the same. I'll tell you in a minute. That's how he did the topological spaces, right? That's the algebra part. But what McKinsey and Tarski did was, as I mentioned before, power set algebras are complete Boolean algebras, right? Instead of just working with power set algebra, that's what we usually do. When we are trying to make everything algebraic, we are generalizing things. So they generalized it for Boolean algebras with an interior operator instead of just power set algebras, right? Like we can just generalize it to Boolean algebra. So what is an interior operator? If you have already seen topological spaces and the interior in it, it's very similar to that. We're just generalizing that. So it's a function, you can think of it as a unitary function from B to B, where B is my Boolean algebra. And box 1 is 1. 1 is the top element. So if you have a lattice, the 1 is the maximum and 0 will be the smallest. So box of A needs B is box A needs box B. And box A is below A, and box A is below box A. So these are the conditions an interior operator satisfies. Oh, actually, from this I get the monotonicity. Like if A is less than B, box A is less than box B, and I can apply that here. Because I have box A is below A, I can apply box A is below box A, and with those two conditions I get equality already. So yeah, that's true. So this is actually equal. So what I mean to say is when you apply the box 2 times, it is just fixed. So what are closure operators? Closure operators is just the dual of interior operators. You have a box, you negate it, then you just get the dual of that. That's the closure operator. So an interior algebra is a Boolean algebra equipped with an interior operator, and this was what done by Mckinsey and Tarski. And let me just remind you, this need not be complete here. Interior algebra is just a Boolean algebra with an interior operator. So this is exactly how Mckinsey and Tarski did, but they did it with closure operators, not interior. They are one and the same for me. And Razio and Sikorsky, they just started working with interior operators. They moved from closure to interiors. And then the name interior algebra was given by Bloch. So what is a Mckinsey-Tarski algebra then? It's an interior algebra, but the Boolean algebra associated with it is complete. It's a complete Boolean algebra with an interior operator box on it. So we had a Boolean algebra with an interior operator. We just made it into complete because, as I mentioned in the beginning, our driving force was the power set algebra. Right? Power set algebra is complete. So complete Boolean algebra. And the morphisms is just complete Boolean homomorphisms with this condition h of box A is below box of HA. I will explain later why did we choose this to be half preserved and not equal to. Why is H box A is not equal to box HA, but it's just less than or equal to. I'll just explain that why we chose this.
Complete really satisfies arbitrary.
Yes, exactly. Both. Yes. Yeah, complete yes. Arbitrary meet, arbitrary join, and Boolean, so negation is also present. The category of MT-algebras and MT-morphisms, I'm gonna just denote it by MT. My pronunciation is bad, it's MT, but people always hear it as MT, so just don't get confused. Algebras can never be empty. And then once this gets preserved only when it is an isomorphism, the complete Boolean isomorphism, then the box is preserved. Okay, so now we have topological spaces, we have frames. Now I define what MT is. So how are we going to relate all these three together? So we take something called as open elements. What are open elements? It's preserved under box. So I have an operator box. So the elements which doesn't get disturbed by box. So box A is A. So those are my open elements, and I'm going to collect them and write them as O of M. And the closed elements similar, but instead of box, it's the diamond one and C of M. I think if you have a topological background, you would have seen open sets interior of A is A, closed sets C A closure is A. So I'm very similar. Opens, closed. So again, we need functor to travel between the worlds, right? So that's the story here. So when I have an empty algebra, I can take the open elements and I get a frame. And I say something which is, right? It's an essentially surjective functor. What do we mean by essentially surjective functor? You can think of it as a mapping which is surjective map, right? What is a surjective map? For every element in the codomain, you can find an element here. So same fashion, but in the functorial setting now. It's in the functorial setting. So this is an essentially surjective functor. So how did we show that? We use something called as Kunayama envelope. Yeah. So let's say I have a frame L. I want to make it into an empty algebra, so I want to make it complete Boolean algebra. So in order to make it Boolean, I take the Boolean envelope. Okay. Let's just say, even if you don't know what Boolean is, I'm taking something and I'm making it into a Boolean envelope. Now I want to make it complete because my protocol was complete Boolean algebra, right? So in order to make complete, we take the McKinsey extension and then we make it complete. Unfortunately, this construction is not functorial. What do I mean by that? Maybe in object level, it's whatever I explained works, but once you go to the morphism level, everything breaks. So basically, this O, the construction is essentially surjective only for the object level. That's what I mentioned. So it's neither full nor faithful. Again, these are more technical, but yes, so the morphisms are not. Again, the full, you can think of it as surjectivity for the morphisms, not the objects. Faithful, we can think of it as one-to-one function, how we do one-to-one in functions, but for the morphisms, okay? Because category has both objects and morphisms. So now we saw how to go from empty to frame. And now talk to empty. So the relation between topological spaces and empty algebras. So this we already see, the whole motivation was this power set algebra and interior operator. So once I have a topological space, the power set algebra and interior operator is my. And how about the function? If I have a continuous function within topological spaces, the inverse image function, the power set of y to power set of x, is a complete Boolean homomorphism, satisfying as filters of interior of A is inside interior of X. So this was the motivation. Why? In the beginning, I think I mentioned like we preserve it halfway. That's because when you have a continuous function, f inverse of interior of X inside interior of f inverse of A. In order for this to be equal, we need an open map. So we don't have an open map on the topological side, it's just continuous function. So this is just half preserved, and that's what we generalized it to interior. So like every time I do something, I'm just going to do everything in the category theory notation. So P will be my functor, which takes things from topological spaces and put it into the empty world. And it's a contravariant functor such that O proposition P is domain. So this one gives me the relation between all these three worlds. So frame existed, top existed, well known. This is how the empty worlds fit inside these two. So I can go from empty to frame and top to empty, right? But can we go the other way now? Here, top to empty, yes. How do I go from empty to top? Like, is there a way to go back? Of course, yes, we do. So what do we do now to go back from an empty algebra to topological spaces? We look at atoms. Take all the atoms and then we make it into a topological space. I think we have the chat. Should I open it? Yes, it is. They are complementary. Yes, the complement of open is closed. That's a good question. Yes, the complement of open is closed and the complement of closed is open. Thank you for the question. Oh, sorry. Yeah, thank you for the question. So
Yes.
oh, it's here. Yeah, so complement of open is closed and complement of closed is open. For me, complement is negation. Negation of open is closed, negation of closed is open. So yeah, the empty algebra, the atoms will be the set of atoms. So now this is the set, and now I have to define a topology on it to make it into a topological space. So I define a mapping from an empty algebra M to the power set of atoms of M. Something like eta of A. I collect all the atoms below that element. So whatever the element I choose, all the atoms below that element. This is an onto empty morphism. And the topology is just the image of opens under this map. Take the opens, image of that. So again, this is a little bit technical, but yeah, but once you have a complete homomorphism always, you have a right adjoint and left adjoint, right? So when I have a morphism, I can go back. That's like, you can think about it like, if you have a function, we always do the inverse function, right? Inverse function, something like that in the lattice setting, that's like adjoint. So h star of x is meet of A in A such that x is below h of A, this is the adjoint. And I make use of this definition to go from atoms of B to atoms of A. So if I have a morphism from A to B, to go from atoms of B to atoms of A, I'm going to make use of this definition, and this is a well-defined continuous. So the whole story of this slide was, if I have a empty algebra, I take the atoms to go to the topological space. If I have a empty morphisms, I take the adjoint to go to the continuous map. Yeah, so that's what it is. So we have a contravariant functor. So I can go from empty algebras to topological space. So now again, once I say we set up everything, so we have to check certain things in category theory, whether everything is working right. So we are going to define another map from a topological space X to the atoms of power set of X. So the atoms of a power set is just singletons. That's how I define the singletons, and this is an homeomorphism. When I say homeomorphism, this is like almost they're the same. So I had a contravariant adjunction P and AT with these units, eta and epsilon. So I make something called as SMT, that is spatial empty algebra. What are spatial empty algebras? The Boolean algebra attached to it are atomic. So that's all it is. So then I get a dual equality between spatial empty algebra and topological space. The eta I defined in the previous slide is an isomorphism. So these two are equivalent. Okay. Just to motivate, Tarski duality is something complete atomic Boolean algebras and sets. They're equivalent. Complete atomic Boolean algebras sets. So when does something become a topological space? You define a topology on a set, right? I have pretty much done the same thing. When you define a topology on the set, you also define a box on it. So those two is just, this becomes SMT algebras and this becomes topological set. That's what it is. It is really equivalent. Just defining topology on both sides. Okay, now let's compare everything together. This was the frame part, topology to frame, open sets, going back, points, and then there was equivalence between sober spaces and spatial frames. What became special here is I did not have to restrict any topological spaces. So every topological spaces is captured by spatial empty algebras. So in a way, you can think about this topological spaces sits inside empty algebra. Empty algebra is a bigger umbrella now, so this topological spaces sits inside empty algebra. So that's the whole benefit of this, that you can capture all topological spaces, not just sobers. So empty is a faithful generalization. This one was, I wanted to add this because the main reason I'm here in South Africa is because of Colin. His PhD thesis was from UCT, and then someone mentioned to me that he has already done some very familiar flavor of thesis in 1990s, and I went and I looked. That's how I realized like pointer topology is being done. I mean, I think there are more pointer topologists in South Africa than any other country. So as far as I know, so that I really wanted to add that. And that's how I started seeing everybody else, and that's how I started following the Pilar's work and that's how I got it. So he also defined separation axioms, right? But it was in terms of atoms. But what I'm going to do now is, whenever I say MT-algebra, there may be no atoms at all. Because atomic, the ones which are atomic, I call it spatial empty algebras, right? So that means I can have an empty algebra without atoms at all. There may be no atoms. So I cannot talk about atoms when I'm doing separation axioms, which is quite difficult, right? Because atoms are just points. I cannot talk about it. So how do we generalize it? So a subset of a complete lattice join generates if each element of this join of elements. It's just some definition, join generates. So why this is important?
Want to write, you need to annotate. Can I just write there?
I'm stupid, but not that stupid. Okay, so like if so far I hope I have concluded that every element of my empty algebra we have to be thinking like a subset, right? Subset. So let's say I have a subset A, some topological space, and some subset A, right? So I can write any.
For this, those watching online, actually, no.
It's okay. I can just.
Or you can like annotate and you can use the blank space. Right? Then look at your left. Ken has been chosen, your left. So now you can write. I think it will work.
Okay. So I have a topological space X, and let's say I have a subset A, right? I can write A as union of all the singletons X in A. Right? It is just collection of all the elements, any set, right? So this is the motivation why we are going to do this. But let me remind you, these are atoms in a topological setting. But my MT algebra may lack these things. So when I say join generates, I'm going to see how these singletons behave in every topological space and make it join generate. That is this union, right? Join generating that, looking at the certain kind of elements. In this case,
Annotate here. The menu will come up and you can pick up all drawings. I think it's annotation. Now it is done.
okay. So what are T-naught algebras? So if you remember, I had something like singletons, right? But I don't have singletons now. So instead of those singletons, what I'm going to do is replace with meet of opens, meet closed. That's exactly how the singletons behave in the T-naught algebra. If you have a T-naught topological space, the singletons would look something like this. Because in the MT algebra I may lack the atoms, I'm going to replace it with something like this. Meet of opened, meet closed. So they are the ones join generating the M, and that's my T-naught algebra. Okay. If you have already seen topological spaces before, so the singletons of a T1 space are closed. Yeah, every singleton of a T1 space is closed. So, but you have union of singletons. That means you have union of closed, right? That was T1 case. So, but for T0 case, instead of closed, we have the special looking ones. So, it join generates. T half in the topological setting means every singleton is meet of open and closed. So I'm going to generalize it to open and closed, meet of open and closed. That's T half algebra. So join generates. So instead of singletons, we have all these kind of elements join generating. And T1 algebra, this is pretty easy to connect with what happens with topological spaces because singletons are closed. So T1 algebra are generated by closed elements. And T2 is a very tricky thing in frame theory to explain what Hausdorffness means. It's not very obvious, I would say. So here the T2 algebra exactly the same way. All we have to do is look at what the singletons are doing in the topological spaces. They would look something like this. Every singleton in a Hausdorff space is intersection of closure of open. Okay, that's exactly what I'm doing. Meet of closure of open. So that will give me the default. So these are my lower separation axioms. So I call these lower separations axioms because like I don't have to add anything to from T2 algebra. It's T2 algebra, T1, T1. So these are
Arrow.
So now I defined what T0, T half, T1, everything is, right? But anybody can define, but we should check if it's correct or wrong, right? That's why the category theory helps. This theorem is just stating whatever I defined in the previous slide is a good one. It agrees with everything. So it means we had already developed how to go from MT algebra to topological spaces to MT algebra. Can I still do the same if I restrict it to T0, T half, T1, and T2? Yes. So if I have T0 MT algebra, I can get a T0 topological space. And if I have a T0 topological space, I can get a T0 MT. Same thing for all the others. So now, once we go to the higher separation axioms, they act very similar to what happens in the frames. It's pretty similar to that. So first, let my MT algebra be a T1 algebra. So and it's T3 or regular if every opens is join of opens such that the diamond D is below A. but if you have seen the frame theory, this condition is pretty much like well inside condition, the regular well inside condition. And T3.5, this is completely well inside relation in the frame theory. So for every open, you can find, you can be written as join of open such that B is completely well inside A. What do I mean by that? B is completely well inside A means that there exists collection of elements enumerated by the rational 1 such that B is below A0, A1 is below A, and whenever P is less than Q, box A is AB is less than or equal to box A. Sorry, diamond AB is less than or equal to box AQ. So once we start from T3, in topological spaces itself, it's already point free. Every open can be written like this, so it's already point free. So that's why the higher separation axioms are interesting on its own thing, and it gives a different perspective. But it agrees very well with frames. So what about T4? T4 algebra. If you have seen normal condition, what are normal topological space? It's the same thing. You have CD closed elements such that they are disjoint. You can find open and disjoint open elements such that C is below U and D is below B. When I say disjoint, I simply mean the meet is 0. That's T4 algebra. So again, now we have to check all these conditions are the valid conditions. So we make use of the category theory, and make sure the dual adjunction and dual equivalence we had before will restrict to T3 and T3.5. What I mean, like T3.5 algebra is T3 spaces, T3 spaces. But if you recognize something, I'm missing T4, right? I'm missing T4. So it's not clear whether atoms is necessarily normal or a normal MT-algebra. Consequently, the existence of a dual adjunction will be not normal. Even in topological spaces, normal spaces, the subspaces of normal spaces are not normal, which is a known fact. The subspaces of normal spaces are not normal. It's not hereditary. So similarly, atoms of a normal MT-algebra may not be normal. So it's not a surprise it fails because it's literally what's doing in normal topological spaces. But however, if we make it into a spatial thing, it becomes normal. Okay? This is still an open problem. I don't even have a counter example. Somebody wants to contribute everything. I don't have a counter example. Yeah. Now we want to see that okay, everything is equal in topological spaces. I argued that for a lot now. So now, but also the things we have described are very well behaved with frames, frame theory. So that's why I want to show the Hoffman-Wislov theorem and Skottow-Confield, right? Hoffman-Wislov theorem states that the compact saturated sets of a sober space and the Skottow-Confield filters are equal. There is an isomorphism between these two. So I'm going to show this happens with So M is a sober. It's exactly like how you expect in the topological spaces. I have defined it the same way. Join irreducible closed set. There exists a unique atom. No, not unique atom. There is an atom such that P is equal to diamond of X. And I call something an open filter. If A is in the filter F, implies box A is in the filter. So an open filter is spot open if for each directed family of opens, whenever join of S is in F, we can find an element in S which is in F. That's spot open. I mean, this is exactly what is spot open filter in the open frame theory. Actually, this is more general. Even in the domain theory, we have something called a spot open. So we can denote that by S-filt, spot open filters. And a compact, as you would expect, it's the same thing. Whenever A is below join of open elements, you can find finite open elements as A is below join of finite open elements. That's compact. And saturated simply means meet of open elements. Exactly like saturated sets, which is intersection of open sets. So once I have that, This is K-sat, that is compact saturated elements. And once I have that, we can actually prove for M is a sober empty algebra, spot open filters are isomorphic to compact saturated elements. So the same thing happens in the frames, right? In frame theory, from this we can derive this actually. Spot open filters are isomorphic to compact saturated elements of points of L. And in the topological spaces, same thing. Spot open filters of opens are isomorphic to compact saturated of X. So the only thing I want to mention here is, if you remember in the beginning, this is the functor, pt is a functor, points is a functor, and omega is a functor. So in both these theorems, I'm using functors to find this equivalence or to find this isomorphism, right? In the empty algebra, I don't have to leave the empty algebra world. I get everything in empty because I don't use any functor. So just to remind, functor is go from one world to another world. Here you have to go to the topological setting. Here you have to go to the frame setting. But because this captures both frames and topological spaces, I can just get the isomorphism directly without leaving the world. So now, using Hoffman-Miss law theorem, we are going to derive some of the dualities. This is just to, again, this is too categorical, but I'm going to try to just go quicker. So this is important because what is a locally compact topological space? For each open set U and an X in U, there exists an open set V and a compact set. So we say something is locally compact if this happens. X is in V, V is in K, K is in U. So what do we do algebraically? We take the sets and we generalize everything to the point set, right? That's exactly what I'm going to do now. And this is exactly what I do. I define a relation. A is related to B if there exists a compact element in between them. Just mimic this. Yeah? You have A related to B, you can find a compact element in between them. That's what I'm going to define a relation. So I call something is locally compact if every open is join of opens B related to B. Okay. Locally compact is very similar to what happens with frame theory, continuous. Okay, we will go see that. Before that, a continuous map is proper if F inverse of compact is compact oscillated is again compact. Similarly, I have an empty morphisms. It's improper if a compact saturated goes to compact saturated. You can see, if not anything, at least I want you to take away this from the thing, like how everything set can be just generalized to algebraically. Everything is literally the same thing. The compact saturated set became a compact saturated element here. Okay, like this one is continuity. Continuous just means there is a frame which, let me define what way below is. A is way below B, provided whenever B is below, let's say directed join of S or join of S, I can find a finite subset of S such that A is below join of B. So when I say something is continuous, if A is join of elements such that the element B is way below A. So and the frame homomorphism is proper if it preserves this way below relation. So now this is just the defining the. Okay. So once I have defined all the categories, I can get an adjunction between locally compact sober empty algebras and continuous frames. Here, I just want to make a note. The equivalence, to get an equivalence, I have to add spatiality. Those of you have already seen frame theory before. Continuous frame implies spatial. So it is not true in general. Locally compact sober empty algebras are not spatial. I'm just advertising my next paper. This is not something. Continuous frames imply spatial is not something like it is true, but it is just a coincidence. Because frames cannot capture T naught. It's just like hiding the fact that it's just like a result that it is spatial, but it need not be true. And locally compact sober MT-algebras we need not be special in our counter exam. Okay. So now there is an equivalence between, from this we can get an equivalence. So this is, we can derive the Hoffman loss and duality. The continuous frames are equivalent to locally compact sober MT-algebras. So now something is compact if the top element is compact. And then similarly, by defining all this, I get a equivalence between compact house dot and compact regular. And this is its best duality. Its best duality says compact regular frames are equivalent to compact house dot, and I get this using the MT-algebras. So this we could have done even with locally compact. We didn't even have to go to the compact one. We could have done with locally compact. This is what I explained compact. We could have just got it by local. And I think I'm running out of time, so I just want to generalize everything so far what I've done before I continue. Yeah, this is the whole duality. Just because I like this picture. So locally compact, continuous, locally compact sober, and locally compact house dot, continuous regular, locally compact house dot. So what I am highlighting here is we can't do house dotness in the frames, right? So it's continuous regular, but we can pretty much do house dot in MT-algebra. The same thing we can do similarly for stone spaces, which I skipped in. And but the last thing I want to conclude is doing the stone duality, because stone duality is what was the first point-free version of doing duality by Marshall Stone. So I'm going to do the same thing in MT-algebra. So I take the canonical extension of a Boolean algebra. Given a Boolean algebra, we all know how to do stone duality, right? We take the ultra filters. So I'm doing the same thing, but now I will take the power set of the ultra filters to get the to get the canonical extension. But now we are doing everything generalization. We're not talking about power set. So canonical extension is just a complete atomic Boolean algebra, such that there is a Boolean embedding, which satisfies some conditions. And we can also define a box on it. And this is the stone MT-algebra, so that now I can get a equivalence between Boolean algebra and stone MT-algebras. Very similar to what happens with Boolean algebra. Stone spaces, we have Boolean algebras. Boolean algebra is very important. And we can get this corollary from this result. Thank you.
Thanks for Ranjitha. We also welcome questions from the online audience.
About